thank you very much for inviting me, particularly Neil, because it's largely him that got me here. And apologies to the rest of you for the fact that Neil has invited me here. This is going to be a slightly strange talk, so I should probably manage your expectations a little bit. During the course of the talk, I'm going to advocate a set theory in which none of the axioms of ZF hold except extensionality, union, and pairs. And to be honest, I'm a little bit iffy about pairs, but you know, I'll probably allow that one to go. So this is obviously in some sense a slightly cranky talk, but I do mean it seriously. I don't mean in advocating the set theory to say it should be used as the one true set theory, but what I do want to do is suggest that it's in a surprising way an excellent rival to more standard pictures like the picture you get from ZF. But it's a very elementary talk in the sense that I'm not going to be talking about anything sophisticated in set theory. There's going to be no complicated gadgetry. It's all really based at the levels of what axioms should we want to accept in the very first place, rather than what can we do with those axioms. But ultimately, the reason that a whole bunch of axioms that I've just mentioned to you are going to fail is because I want to advocate a set theory which allows for a universal set. So that's the overall picture.
You're not advocating this as a form of foundations of some kind?
Well, it will work just as well for your foundational purposes as ZF if you want it to, as I will explain in detail. Okay, so the structure of the talk, there are 4 sections to it. The first one is just a kind of motivatory spiel, just explaining the big idea and why I think that we ought to love the universe, i.e. love the universal set. Then in the second section of the talk, I'm going to have to just recap a few things about how we should think about the ordinary notion of set in a slightly different way. Then in the third section of the talk, I'm going to talk about my new way of conceiving of sets, which allows for a universal set. And then in the fourth section of the talk, I'm going to describe how you can interpret back and forth between these different set theories, and thereby actually partly answer Sai's question just then about why it actually would work as a foundation if you wanted it to. Okay, so the first section, though, is about why we ought to love the universe just at a sort of motivatory level. So the big idea that I want to convey in the set theory that I'm going to embrace is that you should think of sets not just as collections of objects, but as partitions. And what happens is that you affect a partition in the universe, and both sides of that partition give you a set. So when you choose, for example, the set of cows, you also thereby form the set of all the non-cows. And if you form the set of natural numbers, you also thereby form the set of all the things which aren't natural numbers. That's the basic idea that I have of sets, and obviously it's not something which is built into the standard conception of sets. In fact, it's immediately rejected by the standard picture of sets, because concretely this comes down to the following proposal: every set should have a complement. And by complement, I mean a complement in the absolute sense. So when I say you form the set of cows and thereby form the set of all non-cows, I really do mean all non-cows. So I'm going to use this notation in the talk. I'm going to write the complement of a set just by drawing a bar on top of it. So given a set A with a bar over it is the set of exactly the things that weren't members of A. And the idea is to have a set theory which vindicates this axiom of complements, that for every set a complement exists. And in particular, and so this can be a sort of focal case, but obviously I want it to extend more than this, I want to say the empty set exists just in case the universal set exists, and that's immediate because the universe will be the complement of the empty set, and vice versa. So one way of bringing out my question as to why we don't accept a set theory which has the axiom of complements built into it is, why do people always say, oh, the empty set, we're perfectly fine with that, but we don't believe in the universal set? So that's a way of sort of setting up the structure that I have. Okay, so I think the most important argument, I mean, there are a bunch of arguments that people give as to why you should believe in the empty set and not the universal set. I think the most important argument is that it's a consequence of our best conception of set that only one of those two exists. So you should love the empty set because it's formed at the very first stage of forming sets, and you should shun the universal set and say it doesn't exist because it wouldn't be formed at any stage, because it would have to come after all of them, but it would have to be formed at a stage, etc. Familiar reasoning. I think that is a good argument. Admittedly, this talk about forming sets stage by stage is something of a metaphor, but it's a metaphor which is very important in a bunch of different ways. So familiarly, it gives you a powerful technical tool. If you conceive of sets as stratified into well-ordered stages, then you can do induction on membership, and induction on membership is a very powerful tool. Equally, this idea of stratifying the sets into stages gives you intuitive confidence in the consistency of the theory. So why do I believe that ZF is consistent at all? It's not because no one has yet found a contradiction. It might just be that the contradictions are very hard to find and no one yet knows how to do it. The reason I'm confident in the consistency of ZF is that I can see it as a way of realizing a picture of sets as formed stage by stage, and that stage by stage constructive kind of process makes me think probably there isn't going to be a contradiction to be found. So there is a serious challenge here, which is if you want to believe in the universal set, can you arrange the sets into stages in a similar way whilst delivering on the existing? And in this talk, I'm going to accept that challenge, building on some work back in the 70s, simultaneously but separately by Alonzo Church and Urs Oswald, and then some recent stuff by Thomas Forster. So that's the overall strategy, to give you a set theory which puts the sets into well-ordered stages, but also gives you a universal set.
Wait, so the universal set would also appear at one of these stages?
Yes, in fact, it will appear at the very first stage. We'll find out. Yep. Okay, so in order to do that, though, I'm going to run through just a couple of other things, because basically my plan is to take the ordinary process as we describe it, offer you a nice axiomatization of the ordinary process, which may or may not be familiar to you. It's certainly not ZF. And then deform the axioms that I get from that so that they give you a universal set and everything else. So this next section of the talk is in some ways just recapping the ordinary notion of set, but from a slightly different point of view. So just to remind you, the ordinary notion of set, I feel like I may be teaching grandma to suck eggs, but the ordinary notion of set can be pithily summed up in a bunch of different heuristics. But here's one I particularly like from Schoenfeld. This is 1977. So sets are formed in stages. For each stage S, there are certain stages before it. At stage S, each collection consisting of sets formed at stages before S is formed into a set. There are no sets other than sets which are formed at stages. It's a nice way of picturing things, and it's this kind of story, as I said, which makes me confident that set theory is consistent.
It doesn't say stages are long.
No, he doesn't say they're well ordered. Glad you mentioned that, because one of the basic questions I have is, why should we even assume that the stages are well ordered? It will turn out that we can extract the well ordering as a theorem from the theory I'm going to give. So that's actually a result by Dana Scott, basically. But yeah, so what I'm now going to do is take that story, turn it into some axioms following things that Montague and Scott did, some of which was unpublished. Boolos's famous papers on this, which draw an awful lot more on Scott than I realized originally, and then some stuff by Derrick and Michael Potter. Okay, so here's just me extracting a little more juice from the story, 5 principles which I think ought to be true given the way I told the story. First principle is that sets are extensional. Okay, I didn't actually mention that in the story, but I take it that's going to be analytic. If we're not talking about extensional collections, we're not talking about sets at all. I trust the fact that I'm at least going to give you the axiom of extensionality will make you slightly comfortable, given that I'm, in the end, not going to give you any of the other axioms. The next axiom is that before is a transitive relation on stages. Again, we didn't say that explicitly, but I take it the whole idea of speaking temporally is meant to be that we're allowed to bring in some of the notions of a temporal order. And certainly as we ordinarily talk about the notion of something's being before something else, that's a transitive relation. If A is before B is before C, then A is before C. Third principle, a set is formed at a stage if and only if all its members were formed earlier. That should be intuitively acceptable, because I said at each stage you form sets of arbitrary bunches of stuff that you had available earlier, and that's the only way in which you get to form a set. So this biconditional should be true. And then another principle, for any stage, the set of f's which you formed earlier exists for any property f. That should, again, be intuitively acceptable, because one of the things I said is take together any of the sets that you had available earlier, in particular take the f's, lo and behold, you form them into a new set. Final principle, every set is formed at some stage. That was just one of the things I stated explicitly. Okay, so those are 5 principles I think you get from the story. The last 3 are explicit, the previous 2 are implicit. Still, by the way, I haven't said anything about the stages being well ordered. For all you know, they might be dense, They might be going back infinitely. Who knows? I've just laid down these principles. So the next stage for generating an axiomatization of this is to write down axioms using as rich resources as you could possibly help yourself to. So what I'm going to do is turn these 5 intuitive principles into 5 axioms in a two-sorted language with a couple more primitives than you would ordinarily expect to see in a set theory. So it's going to be a theory called stage theory with sorts, because it's two-sorted, and stage theory because I've been talking about stages explicitly, and we write down the following axioms. So the first one, obviously we know how to formalize extensionality. There's no surprises there. Second axiom, before, is a transitive relation on stages. So I've said for any rho, sigma, and tau, if rho comes before sigma comes before tau, then rho comes before tau. So I've introduced new sorts of variables for stages. I'm going to use Greek letters for stages, and I'm using Roman lowercase italics for sets. Okay, so these are just 2 distinct sorts of objects, never the twain shall meet. And of course, I'm reading this less than sign as being before. So you just read that as take any stages, rho, sigma, tau. If rho, sigma, and tau are in that order, then rho comes before tau. Okay, no real surprises there. Pretty easy to write down an axiom governing this biconditional. A set is formed at a stage if and only if all its members were formed earlier. For any stage and any set, A is formed at that stage, that's how I'm reading that little circle, is formed at, if and only if for all of its members there was some stage such that that member was formed at that stage and that stage came before the stage at which A is formed, and vice versa. So that's just helping myself to a new primitive, X is formed at stage rho, and just writing down things in the most naive way that a set is formed at a stage if and only if all its members were formed earlier. Yes?
Why is it if and only if like an essential part of the story? Because there's natural hierarchies that we deal with in set theory where this where you can form something a little after all of its members show up in a stage.
Oh, yes, sorry. You should probably read that as formed, first formed at.
Okay.
So you'll keep forming it over and over again at next stages if you want. Does that answer what you had in mind? Sorry.
But
so this would be a least stage where the set is formed?
I haven't yet said that. No guarantee of that. It may be that the stages go infinitely downwards.
You form a set over and over again at each stage after the stage where all its elements.
It's like it keeps getting reformed, right?
Yeah, sure. I mean, I don't really mind whether you say that.
The stages are linearly ordered, at least.
Haven't yet said that.
It's transitive.
All I've said is transitive. Don't worry, you will get these things out. But I think one of the interesting things about this is precisely that it doesn't look like I'm telling you much about the ordering relation at all. But I can in a moment. So in a moment you'll see that it turns out you can prove from this that the stages are well ordered, which is remarkable because it really doesn't look like you ought to be able to from these axioms.
But you have to form the set immediately when you found all of its members.
If all of its members were available at some earlier stage, then indeed the set is available at that stage.
It's available, but does that mean like you had to build it at that stage?
Yeah, so it certainly gets formed at that stage. And it can be reformed multiple times. Okay. I'm fine with that. Okay, just moving on for the last couple of axioms. So this is like a separation principle. I've written it out in a second order form because second order logic is great, but if you would prefer, you could rewrite it as a first order scheme in the obvious way. So take any property, any stage, there is some set which consists of all the F's formed earlier. That's basically using exactly the same notion of formed earlier as I was using in the previous axiom. So this just writes down a principle of separation on stages intuitively. And then the final principle was every set is formed at some stage. That's very easy. For every set, there's some stage such that the set is formed at that stage. Okay, so these are 5 axioms in a multi-sorted, multiple different primitive predicates theory. The next trick, yes?
Maybe I'm doing things silly again. Shouldn't the principle, the SS, fall out with SA?
No, it doesn't. Provably, definitely doesn't. Yeah. I get why it intuitively ought to, but you definitely need it as a separate axiom. Otherwise, you won't get anything like the rich power. I mean, this is basically our separation principle, so it does a lot of the hard work in terms of motivating stuff. Okay, so the next thing to do is, this is clearly this theory is sound of the earlier process because, you know, I told you a story, I extracted 5 principles, I've now axiomatized them, but it's also a pain to work with because it's multi-sorted, it's got multiple predicates. The next thing to do, of course, is to reduce it down to a one-sorted theory with a single primitive predicate for membership, because then it will actually look like a set theory rather than a theory of certain objects called stages and certain things called sets. And it turns out that you can get from the theory I've just given to a one-sorted theory with just membership using just the following axioms. So we'll call it LT for, oh, there shouldn't be a Boolean in there, sorry. LT for level theory. We'll come to Boolean level theory later. That's a slight spoiler. It has only 3 axioms. First is the axiom of extensionality, no surprise. Second is a principle of separation on levels. So this tells you for any property and any level S, and at the moment I haven't told you how to really understand that predicate is a level, there is an object which consists, whose members are exactly the Fs that were a member of that level. And then a principle which essentially gets at our hierarchy thing. For any set, there is a level such that the set is a subset of the level. Roughly what happens is the is-formed-at predicate gets turned into a subset principle, and is-formed-before gets turned into membership, and then we also have this remaining predicate is a level, which I need to say something about. So here's the definition of a level. So the first thing to do is to take an operation, and this is due to Montague and Scott. You take an operation which you can think of as the sublative closure. It's not quite the transitive closure, it's a sublative closure, in that it takes a set and it includes all subsets of members. Not all members of members, but all subsets of members. That's what that paragraph sign means, the pilcrow, and that's the notation they used, and I want to stick to it. Then you define the notion of a history. Intuitively, what a history is it's a collection of a well-ordered sequence of things which are going to turn out to be stages. So the history is defined as all of its members are transitive, and when you intersect any of its members with the thing you had and then close it in this sublative way, you get back what you started with. And if you just think to yourself, what would happen if I took an initial segment of the hierarchy and I asked myself, well, is it true that all of its members are transitive? Yeah, because those are all transitive and good. What would happen if you intersected an initial segment, one of the stages of the hierarchy, with an initial segment of which it was a member? Well, if you then closed it under taking all of the subsets, the sublative closure, you'll get back where you started. So there is sort of intuitive motivation for this. And then you say that a set is a level just in case it is the sublative closure of some history. And that corresponds to the intuitive fact that if you have an initial segment of the hierarchy and then you do a sublative closure operation on it, you get out a level. It turns out that if you just write down those 3 axioms with that definition, you can prove from the multi-sorted theory that I wrote down these 3 things. They come out as theorems. So this is clearly also sound of the original process, which is good. Now, here are some further things we can prove. The levels, as I've just defined them using that definition, are well ordered. That's a kind of surprising fact because it doesn't look like there's something like well ordering built into it. We didn't assume well ordering. It falls out of doing some clever stuff with your separation principle, and I should say the proof of that is wholly due to Dana Scott. So maybe you shouldn't take my word for it, but take Dana Scott's word for it. Although I've offered a different axiomatization than him, I haven't screwed up that bit of the proof. It's also, as I've just said, the theory I've given you with those 3 axioms is sound of the ordinary process, but it's also, in an important sense, complete of the ordinary process. What do I mean by that? Well, it categorically determines every aspect of the process, except it doesn't make any comment on the process's length. So you get out a powerful quasi-categoricity theorem for this kind of set theory, namely, it can run for any ordinal sequence that you like. It makes no comment at all on that, but however far it happens to run, if you have another sequence which runs at least that far, the 2 sequences will look identical. So it's just like a standard Zermelo-style quasi-categoricity result, except Zermelo says you have to have your models being inaccessible cardinals, whereas mine can be, your models could just stop at the 4th level, or they could stop at the omega plus 12th level, or whatever you want. It's a very permissive set theory in a certain way. So it tells you everything about the process of set forming, whilst remaining silent on its length. So it's a very nice theory, and one of the things I wanted to do just briefly is let you know that there is this lovely theory out there which has this lovely property associated with it. It's just a fairly, it's an I think significant simplification of the system that Michael Potter has in his book Set Theory and Its Philosophy, but it's very much derived from that and the unpublished stuff by Montague and Scott that Michael didn't know about when he wrote his book. Sorry, there was a hand there.
Yeah, does the first proposition depend on
Full second order logic?
Yeah.
Yes, it does, in the sense that if you want to do it Zermelo style, then indeed, just as with Zermelo, you have to use full second order logic to make sure that your power set really is power set, basically. You don't have a power set axiom, of course, but you know what I mean.
If you replace the second order separation principle with the schema.
Yep. Then in just the same way as you couldn't prove the quasi-categoricity for...
The stages are definitionally definably well ordered, or?
So it's a
You can think of non-standard models of that.
Yes.
It's going to look like this. If you don't have the second order aspects, then it could look like that.
Yes, indeed. So just to clarify, the proof of well ordering does not in any sense depend upon using a second order principle.
Okay.
So it's internally provable. The proof of quasi-categoricity does require essential second-order resources. So yeah, this is the only stage at which I'm actually relying upon the second-orderness, but it's just, in some ways, it's just to make it more familiar to you in a way. The other thing I would say is you don't need, there's also like appropriate internal quasi-categoricity results, but maybe I'll just hold off on saying anything about them because no one cares about internal quasi-categoricity except probably you and me, and we can just discuss that later. Anyway, this is not the main point of the talk. This is just to say you can do all of this stuff, and it gives you a very nice set theory. In some ways, I think it allows you to frame all of the other axioms of set theory that were in any way interesting or philosophically controversial very naturally, because you can now just look at the other principles and say, well, we've already got the hierarchy of sets set up just right. Now we can ask questions about, say, its length, in other sorts of ways. But I don't want to go to the wall for that, so I just wanted to give you this. What I'm now going to do is deform this into a different set theory. So this is the next part. Yes, sorry.
Could you just give us an intuition of just why is there a minimal level?
Yeah, so what you do is you define a set as being grounded if and only if it's only a member of well-founded sets in the normal sense. So you just define well-founded in exactly the normal way. And then a set is grounded in case it's only a member of well-founded sets. Then you use separation on your stages to give you the grounded subsets of stages. And then just because grounding turns out to be quite a nice property, you can show that those things must be well-ordered, and so get the well-ordering of the stages via that route. That's the rough way it works. And I can, yeah. If you want, the idea for that is in a paper by Scott from, it was published in the mid-70s, but it was presented in 1967, I think. But yeah, that's the rough idea. You come up with a clever use of separation. Okay, so now I want to move on to the excitingly different set theory, though, which gives me a universal set and the sets as well ordered, and a Boolean algebra of sets. Hooray. Okay, so here's how it goes. I'm going to tweak the original story. So we had Schoenfield's explanation of it earlier. I'm going to tweak it very slightly to describe a different process, which I will call the complemented process for reasons that will become clear. Sets are found in stages. Quick pause. I didn't say formed, I said found. There's a slight bit of trickery here as to why I'm saying found rather than formed, but my justification for it at this stage is that I don't want this to be thought of as too constructivist a metaphor. Talking about forming them makes it seem very constructivist. Think about this instead as a process of discovery rather than a process of creation, so that it's at least compatible with Platonism. Not that I particularly want to say you should be a Platonist or otherwise, but I'm just going to tweak the story slightly. Okay, sets are found in stages. Every set is found at some stage. At every stage, and for any sets found before it, we can find a set whose members are exactly the things that we had available to us before, and also a set whose non-members are exactly the things available to us before, but we find nothing else at that stage. So all I've really done is tweaked the story by adding this clause H. If you got rid of clause H, you'd essentially have Schoenfield's story, but you with a very slight tweak about talking about finding rather than forming. But that's all the change I'm going to make. And I should say explicitly that this is adapted from a story that Forster tells in a 2008 paper. And what he's doing is trying to make sense of some stuff that Church did on the universal set in 1974. Okay, so now all we need to do basically is run through exactly the same sorts of processes as we had before. So I had a story. I'm going to turn it into a theory which has lots and lots and lots of different sorts and predicates available, and then strip it back down to a single sorted, single predicate theory which would deserve the name of a set theory. First, just a little bit more commentary, just a little bit of intuition about how this works. So we start by finding the empty set. At least that's going to be available to us if anything is. I shouldn't at this stage say that we should assume that this is a well-founded process, but we will later prove that it is. At the same point as we find the empty set, we must of course find the universal set, because if we find the empty set using clause L, then we find the universal set using clause H. Then at the next stage, we collect together all possible collections of things available to us earlier. So we form the singleton of the empty set, the singleton of the universal set, and the doubleton of the empty set and the universal set. But of course, we also find their complements using clause H. So we find the thing which only omits the empty set, which only omits the universal set, and which only omits both the empty set and the universal set, and so on. And I have to say and so on at this point because, as Forster nicely points out, here's the formula for calculating the number of sets you've discovered at each stage in the hierarchy. So at the 0th stage, you find 2 sets, the empty set and the universal set. And then at subsequent stages, you find 2 to the d alpha plus 1 things. So the next stage, you will find 512 sets. And then at the stage after that, you will find 2 to the 513 sets. And then there's no easy way to explain what happens for later stages, but it grows very quickly, so I can't write down any more examples. But anyway, hopefully you get the intuitive idea, and I'm sort of sketching this out there for you like the fact that this is clearly going to end up being a Boolean algebra of sets. Okay, so just a few things to comment on. As I said explicitly, every set is found using one of the 2 clauses, L and H, and now I should probably explain to you why I used those names. If you find a set using clause L, then you obviously find its complement using the other clause. So that's just built in explicitly. I said you find one that has only these things as members, the other one has only these things as omissions. So we're going to call the sets found with clause L the low sets, for want of a better name. That's essentially Church's term, although he uses it for slightly different purposes. And the intuitive idea is you should think to yourself, these things found earlier are in this set, and the limit case of the low set is the empty set, because these things found earlier, you didn't even bother to find any of them. We'll call sets formed with clause H, or found rather, sorry, with clause H, high sets, again just a label, and you should just think these things which we found earlier are the only things which are omitted from this set, and the limit case is of course the universal set. You don't bother to omit anything from it. But just one thing to emphasize, although I'm talking about low sets and high sets, they are both kinds of sets. They are fully extensional. The axiom of extensionality is going to govern all the sets, and there's going to be only one membership relation. It's not like I'm talking about, as Neil and I have chatted about, red sets and blue sets, and there being different principles of extensionality governing the red membership relation and the blue membership relation. There is just one membership relation here, and these are all sets. Also notice I haven't said anything yet about whether you mightn't find a set as both a low set and a high set. So you might just happen to find it at one point with clause L and another at clause H. It turns out that must never happen, but I don't say that at the outset. So what do I say at the outset? Well, building on my story, again, I'm going to give you some principles. It's a more complicated story, so I'm going to need to give you 8 principles, but they're not essentially more complicated than the principles you got for the original process. So the first principle, as before, sets are extensional. Going to take that as analytic of the concept of set. Second, again, before is a transitive relation on stages, because I'm still talking about a stage-by-stage process. I've only tweaked certain aspects of Schoenfield's story. Third principle, a low set is found at a stage if and only if all its members were found earlier. That's just like one of the principles I had for the original story, except that this time I have to say that the set is low if and only if all its members were found earlier. And that reflects the fact that clause L is the clause you use for discovering sets with that property. And then there's a dual principle. A high set is found at a stage just in case all the things which it omits were found earlier. So if you were happy with one of those principles, you should be happy with the other. Similarly, we have a kind of separation principle. So for any stage, the set of f's which you found earlier exists and is low, because if you think about the way in which you do the formation, you say, oh, I've got some F's available to me earlier, I'll collect them together into a set using clause L. Okay, so it must be a low set. And then similarly, for any stage, the set which omits all and only the F's which you found earlier, that will exist. And it's high, that's just the dual principle. And then two more principles to finish. Every set is found at some stage, that's one of the things I told you explicitly. And then a further point, every set is either high or low, and that comes out from the fact that the only methods I've given you for finding sets are clauses L and H. So all of these principles are intuitively sound of the story that I've told you. It's just codifying things in a bit more detail. Next step, of course, is to write down axioms which govern these things using a multi-sorted language and lots of primitives. So there aren't really any surprises here. Now you know how to do it in the ordinary case. So let's say BSTS, for Boolean stage theory with sorts, Boolean because the sets are now going to form a Boolean algebra, goes through all of those 8 principles and writes down axioms for them. So the first things are obvious. Sets are extensional exactly as before. Before is a transitive relation on stages. We already know how to do that. Next principle, a low set is found at a stage if and only if all its members were found earlier. Well, this is exactly like the principle that we had before for a set is found at a stage if and only if all its members were found earlier, but we relativize it. We say that we're only talking about the low sets here. So low is going to be a primitive predicate of this system. So you should read A as low as, well, you should read low A as low. I don't think I actually paused, sorry, to explain the colon notation. That's just an abbreviation for, is there some chalk? Oh, yep, that's a chalk. So if I write for all x, phi, oh, what I mean is for all x, if phi holds of x, then lowercase phi. So it's just a way of making my second order notation a little bit more compact. Sorry, I should probably have explained that earlier.
You said that for space.
Sorry?
It was written for space.
Oh, okay, good. Oh, okay, good. Well, now it's overdetermined that you understand what it means. Great. Okay, and okay, good. Now we're cooking on gas again. Okay, so you've got your you've now got the dual of that principle, so that's kind of your separation principle. This is like your anti-separation principle, that you get high sets which are going to be emitting. A high set is found at a stage of only if all its emissions were found earlier. Unsurprisingly, you just tweak it very slightly. And you can go through all of the other principles and write down similar axioms for them. I will now leave that to you as an exercise, an elementary exercise of translating intuitive sentences into second order logic in this appropriate setting. Okay, sorry, so you've got, I've only written down 4 of them, but you can get 8 axioms. The next step is to move from this multi-sorted language into a single sorted one predicate language, and that's what I'm going to call the theory Boolean level theory. Now we actually have Boolean level theory, BLT. It has only 4 axioms, which is rather lovely. First is the axiom of extensionality, no surprises there. Second is a principle essentially of separation. That's all good. So the separation principle is exactly as you would expect. For any property and for any Boolean level, I haven't yet told you how to read that, but that's going to be pronounced Boolean level, there is a non-self-membered set. That's essentially the surrogate for a set being low. It turns out you can prove that a set is low if and only if it's non-self-membered, whose members are exactly the F's which were members of that stage. Okay, so you can do separation on these Boolean levels or stages. And when you do separation, you get a low set, i.e. a non-self-membered set. Next principle, it's a principle of hierarchy, which tells you that for any low set, non-self-membered set, it is a subset of some Boolean level. And the final principle is an axiom of complementation. For any set, its complement exists, and the set is low if and only if its complement is high, i.e. the set is self-membered if and only if its complement is non-self-membered. Those are the 4 axioms, and now all I need to do is tell you how to define the primitive that I've written down there being a Boolean level, and that's kind of like the way in which we define the primitive for being a level in the ordinary setting, but it's a bit uglier. So here's the full definition. First, just to remind you of what complements are. Then there's an operation for closing things under complements. then there's this operation here which tells you to essentially do something like that sublative closure stuff. So sublative closure was take anything which is a subset of a member. This says take anything which is a subset of a member if that member was low, and anything which is a superset of that member if that member was high. So it's it needs to be a bit richer. And then you just do similar kinds of things to, once you've got those appropriate closure operations floating around, to define the notion of a level in this setting in terms of the notion of a history. So I have to say, it is not intuitive, at least to me, staring at this, that any of this will work. But it is the case that you can prove, using the multi-sorted theory, that the stages in the multi-sorted theory are essentially exactly what we've defined here as the Boolean levels, and vice versa. So each interprets the other, so hooray, it does all work out well. So we have a single sorted theory with just one set membership sign. There's only one primitive in it, and it's an axiomatization of the complemented process as I described it. Okay, so now just a few more things to point out. The first is, fairly straightforwardly, this yields a Boolean algebra of sets under intersection, union, and complementation. No surprises there. The crucial reason you get a Boolean algebra is because we've got an axiom of complements. But, crucially, this set theory also is powerful enough to well order its stages, which are the defined Boolean levels, as I've been calling them. The proof there is essentially the same as Dana Scott gives, and it generates across into this new setting. But it's important, I think, in this setting not to say at the outset of the story, oh, the stages are well ordered. Even if we thought that that was an acceptable thing to say in the ordinary story, if we're having obviously ill-founded entities like the universal set floating around, it shouldn't be intuitive to us that the process of set formation is itself well ordered. But it turns out it's provable from the principles that I've given you already. It's also, in exactly the same way as our earlier non-Boolean theory, sound of the informal story that I've been telling. So in exactly the same way, it's complete. That is, it categorically determines every aspect of the process. You can offer a Zermelo-style quasi-categoricity proof, but it makes no comment on the process's length, unsurprisingly, because I deliberately haven't included a power set axiom or anything like that. Okay, so here's the philosophical upshot that I want to suggest, at least. I've answered the challenge. The challenge was, write down some axioms of set theory which give you a universal set and which order the sets nicely into stages so that you both have the powerful tool of proof, namely induction on the stages, and you have the philosophically important confidence that your theory is consistent. I put it to you that the story that I told about the complemented process is as obviously intuitively consistent as the story that I told, or that Schoenfield told in the first place. So we now have a theory which looks like it ought to be consistent, but it gives us a universal set. Surely, in some sense, this is a preferable theory. After all, we should have wanted a universal set. The only reason we stopped believing in a universal set was because we hit the set theoretic paradoxes and we didn't know how to get a set theory which has a universal set. And then we come along with things like Quine's NF and we say, well, that gives us a universal set, but we don't know whether it's consistent. And it's also a real pain to work with because you don't have this powerful tool of induction on stages. Well, hooray, I can give you all of the things you wanted and a universal set. So you should now all start using Boolean level theory rather than ZF or whatever it was you liked. Okay, so that's the end of section 3, but obviously, now moving into section 4, I need to retract a little bit of what I've just said. Because if it were the case that I needed to tell you all to stop working in ZF, you'd all just tell me to sod off. And kind of rightly so. I mean, it would be kind of ridiculous if I were just to say, look, you were making a philosophical mistake in working in ZF. You need to burn all of that good work and start afresh. That would just be stupid, and I would never actually want to do that. Fortunately, I don't need to tell you all to stop working in ZF. In fact, there are obviously going to be lots of different ways in which what I've offered to you allows me to recapture the work done in ZF. So none of this should come as that much of a surprise, but I now want to talk through some results about how to interpret ZF in my Boolean level theory and vice versa, and that will give you a nicer sense of how all of this stuff fits together. So the first and most obvious point, and this should hopefully be occurring to you already, is that you can recover the ordinary process fairly straightforwardly. Intuitively, I got the complemented process by adding an extra clause in to the ordinary process. So if you just forget about the use of that clause systematically, you'll get back to the ordinary process. At least that's the intuition. How can we make that precise? That hasn't really shown up very well, but what I was trying to do here was point out that also the intuitive picture that I painted earlier gives you a hint of that. The sets that I've highlighted in red are exactly the sets that you would have in the ordinary process. The ones in black are the extra things that are floating around thanks to complementation. Yes?
So if you ignore H,
yes,
you get less than the low sets, right? So if you,
yes.
So if you look at the low sets, do you still have something that resembles?
Yes. So these are low sets,
yeah,
but they are not in the ordinary process.
Not in the ordinary process.
Yes.
If you just look at the low set, you just like.
Yeah, you don't want to do that. What you want to do is look at the hereditarily low sets. Next slide. Okay, so a set is hereditarily low, intuitively, just in case its members are low, and members of members of low, and members of members of members are low, and so on indefinitely. That's obviously the intuitive notion you want to deal with, exactly the question you just raised. Of course, just writing it down with an ellipsis, though, is unsatisfying because we can't just make do with that as if it was a formal definition. Fortunately, we can offer a formal definition. It's this. A set is hereditarily low just in case it's a subset of a transitive set, all of whose members are themselves low. And it turns out that does exactly what you'd want it to. And it's not that surprising, actually, if you think about how to define certain kinds of hereditarily transitive notions and stuff like that in the ordinary context. This is the obvious notion which falls out. Restrict your attention to only uses of clause L ever, so that you're not having low sets with high sets as members, is to restrict your attention to the hereditarily low sets. So, going through that in slightly more detail, we can define the restriction of a formula to the hereditarily low sets just by restricting all of the quantifiers. So you say, instead of saying for any set, you say for any hereditarily low set, and so on throughout. And then what we're going to do is extract ZF within our theory. But of course, ZF tells you lots of things about the length of the hierarchy, right? I mean, the axiom of power sets tells you for every stage there's a next stage, and there's an axiom of infinity, which I haven't given you in my setting, and there's in ZF there's an axiom of replacement, which tells you that the hierarchy is not cofinal with any ordinal. And that's a really powerful principle. So if I'm going to be able to interpret ZF within my Boolean level theory, I'll need to say a bit more about the length of the process. So in particular, I'll add two axioms, two ZF-like axioms. So the first is there is an infinite stage, an infinite Boolean level. I could write down that formally, but what I mean by that is a stage such that it does not come immediately after any other stage, and it isn't the first stage. That's the appropriate way of writing it down. And also a version of the axiom of replacement in its second order formulation here, but you could do a first orderization of this if you wanted. So for any second order function and for any low set, there is a low set which is the image of the first set under that function. Right, so there's no surprises here, it's just exactly what you'd expect. And then this is rich enough to tell you that the hierarchy is not cofinal with any ordinal in the ordinary sense. And so now you get the following result. If you can prove something in ZF, then you can prove that that claim holds when restricted to the hereditarily low sets in this enriched theory. So one thing I can do is say, hey, you who were working in ZF, that was nice. What I should understand you as doing is simply working in the hereditarily low part of the real universe of sets, where the real universe of sets is described by my Boolean level theory, which has complements. So that's an obvious and easy way of interpreting ZF into my Boolean level theory, but there are some other ones which we can throw out there as well. So the next result, and this is sort of more interesting, is that these theories are definitionally equivalent. So can I just check how many of you are familiar with notions of definitional equivalence? Okay, so that is not standard material, so I will just quickly then, I will spend a little more time on this slide. Okay, so here's the intuitive idea of definitional equivalence. Oh, sorry, I should also say some of you may have encountered it under the name synonymy, so calling theories synonymous. Okay, fine. The rough idea is this. Two theories are definitionally equivalent just in case. Each theory can define all of the primitive expressions of the other, such that each theory can simulate the other theory perfectly, and when you combine the two simulations, run them back to back, you get back exactly where you started. So I can't think of any way to put this except this is sort of the tightest formal relationship of equivalence between theories that you might naturally come up with. Here's a very straightforward example of definitionally equivalent theories. Piano arithmetic without the zero symbol as a primitive, and piano arithmetic with the zero symbol as a primitive. Why are they definitionally equivalent? Well, because you can define zero, the constant symbol zero, as it's going to be the very first number. So you know how to handle it using a definite description which you can offer in terms of the other thing. So then one theory defines a primitive of the other one doesn't need to do anything, and then when you look at what they're doing, they are basically exactly the same theory, just with some slightly different notation added. Here's a slightly more interesting example, which might be worth my while just mentioning, because I'll come back to it now. So if you take a suitably rich theory of the natural numbers and a suitably rich theory of the integer numbers, they'll turn out to be definitionally equivalent. And that's not much of a surprise. So if you think about the natural numbers, we've got an initial element there, and then we've got numbers going off here, and then you think of the integers as being like this. All you need to do is, within the theory itself, essentially define a map which does something like this. You map the odd numbers to the positives, and the even numbers to the negatives, or something roughly like that. And because if you've got suitably rich things floating around and coding techniques, you'll be able to describe all of this material within the theory. You can regard yourself, when you move back and forth between thinking of these things as under the ordering of the natural numbers and then thinking about them as under an ordering of the integers, you're really just offering a renotation of the number line. So those are examples of theories which are definitionally equivalent. The basic idea is each simulates the other with as perfectly as you could possibly hope for. Okay, more formally, here's exactly what you would mean in the case of two set theories being definitionally equivalent. So I've got three clauses here which correspond to the intuitive things I've written down there. First, you can define membership relation for each of these. So we talk about an interpretation I and an interpretation J. These are basically just ways of reinterpreting what the various primitives mean. So each of these are set theories, so we need a way of rewriting the membership predicate of one theory as some new, more complicated predicate of the new theory. That's what that clause demands. Then each theory can simulate the other perfectly. What I mean by that is that a theorem of one is a theorem under the interpretation of the other. And then the final thing is, when you put the two interpretations together, you've ended up definitionally exactly where you started. So compounding the definitions next to each other is just the same as asserting the original claim about membership. Okay, so ZF and Boolean level theory with the extended principles which make it run for quite a long time are definitionally equivalent in exactly that sense. I mean, if you like, I can give you a quick sketch of roughly how to think about that, or I can just move on if no one cares. I'll take that as no one cares, so I'll move on, but if we want to come back to it, then by all means, we'll come back to it. So they're definitionally equivalent. So one way of reading that is that formal work in ZF, the theory that you know and love, can be regarded as formal work in my theory, and vice versa, just with a slight change in notation. So I hear you speaking about set membership, and now I say, what you're doing is actually talking about this complicated predicate in my language, but it is purely definable in terms of sets. And you equally can say, I hear you talking about a universal set. Well, actually, I can understand that as just talking about this particular set down here. I think it ends up being something like the singleton of the empty set under the interpretation that I happen to give you. You were just talking about the singleton of the empty set. That's not exciting at all. Just a slight change in notation. We can bounce back and forth harmlessly between these two different perspectives. An immediate corollary, of course, is that the theories are equiconsistent, because if one of them was inconsistent, the interpretation of the proof of inconsistency would be a proof of inconsistency in the other. So if you weren't convinced by my story saying that my theory was consistent, this ought to convince you more rigorously mathematically. Actually, I don't find this more convincing at all, because I still would want to know, why is ZF consistent? And then it would push back to the original question about, well, it's the story that makes me think that it's consistent. But in any case, there's an immediate technical corollary. They are equiconsistent. But there's also a question about how you should interpret the philosophical significance of this definitional equivalence result. Because one thought that you might have is, maybe we should say that although they are definitionally equivalent, Some people at that stage are going to say, because they're definitionally equivalent, it's just a slight change in notation. Really, they are the same theory in some important sense. And I'm inclined to say there might be something to that, but just hold off for one moment. So consider what I told you about the theory of arithmetic and the theory of the integers. There's one sense in which you can say, look, I've got rich enough theories, they are definitionally equivalent. I could regard that as they are the same theory really, just with a slight notation. But a different philosophical perspective is, no, they're genuinely different theories with different subject matters. One of them treats the whole non-negative numbers, and the other one treats the whole numbers, including the negative numbers. So one has as its subject matter only a proper part of the others. Arithmetic, when you're just talking about the natural numbers, has as a subject matter only a proper part of the theory of the integers. You might want to say the same is true in the case of my Boolean level theory and ordinary ZF, that the first interpretation result suggested that ZF has as its subject matter only a proper part of the Boolean subject matter, namely, it only is concerned with the hereditarily low sets. But the Boolean theory is concerned with all the sets, hereditarily low, not hereditarily low, but low, high sets, all of that jazz. I think that's an interesting thought, but now I just want to end by problematizing it and problematizing the very idea of a subject matter in any intuitive sense in this kind of a setting. So, we're going to get one final interesting interpretation result. Again, one which I don't think should be too surprising, but it's quite an acute little result. So take any formula and we'll define its a transformation of it, which involves just negating all of the membership signs and vice versa. So if they were negated, unnegate them, slash them through if they were unslashed through. Okay, here's the final interpretation result. It's a duality theorem within Boolean level theory. For any sentence, that holds if and only if its result of slashing through all of the negation signs holds. So this is not a difficult result to prove. The proof of it builds on something that Forster did in a more complicated setting. But essentially you can define a class-sized anti-morphism of the universe, which just says at each stage, by an induction on the stages which you know are well-founded, do some slashing through of membership signs. There's an anti-morphism in that it anti-preserves structure. It turns membership into anti-membership. So it's quite a cute little result, I think. And it's again, not all that surprising given that the intuitive picture looked so nicely invertible. You'd want to have some kind of invertibility result. And that's what this duality theorem gives you. But I think that this has an interesting philosophical upshot if you take Boolean level theory seriously, which I do, or at least will continue to do so now until the end of the talk. So recall my original picture, that a set should not be thought of as a collection of objects, but rather a partition in the universe where each side yields a set. So I started off saying when you form the set of cows, what you're really doing is partitioning the cows from the non-cows, and each of those things is a set. You are building a wall in the universe. And walls have two sides to them. But as Ursula Le Guin teaches us in The Dispossessed, like all the walls, it will be ambiguous, two-faced. What was inside it and what was outside it depended upon which side of it you were on. So I should just give full credit to my friend Brian King for drawing attention to the fact that The Dispossessed fits in so nicely here. In fact, the origins of this work go back... No, I'm certainly not going to do that. And I'm also not going to turn you into the kind of anarcho-syndicalists that are characteristic of The Dispossessed. But I do recommend you all read The Dispossessed. It's a really good book. But Brian is full credit for both the joke and also getting me interested in this. Literally 13 years ago, we were messing around on a blackboard, and one of us drew a big V because the sets, they're a V. And I was like, yeah, but wouldn't it be cool if instead, and then drew a big X? And then this kind of stuff actually came from that a long, long time ago. So full credit to Brian for that. But the reason that this quote from The Dispossessed is relevant is Ursula Le Guin is pointing out that what counts as being inside and outside depend entirely on which side of the wall you're standing. It's a purely relative matter. And I think this duality theorem gives you essentially the same feature. You can't really tell membership apart from anti-membership, except to know that they are distinct. You can see that there are two sides, but you can't sort of label one as the inside of the set and one as the outside of the set any more than in Ursula Le Guin's case you can label the wall as demarcating an inside from an outside. So Ursula Le Guin's is a variant of the topologist's joke, how do you catch a lion? Well, you draw a circle around yourself and declare yourself to be on the outside. But it's essentially a continuing through of that. So I'm going to spend the last few minutes just running through why I think this is the upshot of the story I've told.
Can I just say, I mean, your dogmatic theorem is much stronger than what you're saying. You're saying it at the level of truth, that you have this kind of flip operator that preserves things. But actually, it's semantic, isn't it? Isn't the universe getting flipped?
Yeah, essentially. I mean, right. So the way I specified it was talking about an antimorphism, which is richer.
Antimorphism, right. So
yeah.
On the semantic level, there's this.
Yeah, I don't know whether I'd prefer to think of that as semantic or just because I'm happy doing everything second order. I just think there is a relation in the second order sense which does this, which performs this operation for you. So I'm very resistant to ever doing semantic assent. Although I have stated that schematically, so I can't really claim that I'm resistant to it. Yeah.
Do you get anything like, this might be a silly question, do you get anything like if you take a model of ZF, and you look at its kind of membership tree as a partial order, and then you take the Boolean completion of that,
then
would you get a model of this?
Oh, maybe. I don't know. I'm going to leave Sai to puzzle that out while I move on with my slides. I can't answer that off the top of my head. No, actually, I suspect, depending on exactly what you want by Boolean completion, you'd need to characterize it under a whole bunch of other things. So the risk is, you got chalk? So the risk is that what you'll do is basically you'll say, okay, here's V, here's my model, and now what I'm going to do is take the Boolean completion. Okay, that gives me something which looks like that. Yeah. But it doesn't give me any real interaction between the elements. So where, for example, am I going to get the singleton of the universe? Simply taking sort of inverse elements for each of this won't necessarily give me that. But I'm not sure. I will leave it to you about how exactly to algebraic structure will be there.
I don't see how what you'll suggest gets a universal set. I mean, this is what you want. You want a universal set.
Yes.
But I don't think this Boolean closure will produce a universal set.
This is one for us to think about more because I will not be able to answer it for sure off the top of my head. You'll get the universe immediately, but what I worry is you won't get the singleton of the universe. But the crucial thing is there's the entanglement between the things. It's not just taking a V and then taking another copy of V and just bolting it on top. It's the fourth. So it's objects like this, a low set with a high set as a member that I think are going to be hard.
Once you form the start sticking more things into the
exactly. And then you'll need to repeat that process through all the ordinals. Yep. Okay, but anyway, so moving on with the result. Oh, yep, sorry.
You said you have a Boolean algebra.
Yes.
Is it complete?
No, provably it's incomplete. So there's a quick proof of that. Quick caveat. For the vanilla theory of BLT, it can be complete because obviously that has some trivial models, like the one which just says 0 and V. So that's a complete Boolean algebra. It's the two-element Boolean algebra. Once you've got anything which looks like an axiom for each stage, there is a stage afterwards, it becomes incomplete. Here's why. So for every set, you can then get to saying its singleton exists. So now just consider the operation where you take the Boolean sum of sets of singletons, all of which have as their only object a non-self-membered set. That will be the set of all non-self-membered sets, but that can't exist because Russell. So yeah, it has to be incomplete. I think that's right. Okay, I'm going to move on and talk just about this duality theorem and the antimorphism result. So in order to try and run through some philosophical ramifications of this, I want to imagine a dialogue between two people. Zoltan advocates the ordinary notion of set. I realize there is a Zoltan here, isn't there?
He's not here today.
Oh, okay.
We have one of these.
Yeah, so I just chose a name which began with Z because I wanted it to be someone who was talking about ZF. But anyway, Zoltan advocates the ordinary notion of set as enshrined in ZF, for example. And Betty, beginning with a B, is going to be someone who advocates my Boolean theory, a rich enough Boolean theory so that they can each simulate each other's stuff and so forth. Okay, so Zoltan says to Betty something like this. There is an empty set, but there's no universal set. Every set is hereditarily low. And it's provable in ZF very straightforwardly that every set is hereditarily low. The question is, how should Betty understand what Zoltan has told her? So Betty's a charitable person. Betty says, well, look, Zoltan has been a victim of miseducation at the hand of ZF enthusiasts, so we need to compensate a little bit for that. We need to be charitable in how we interpret all of Zoltan's claims. Well, there are a bunch of different ways, though, that we can go about doing this. So we can say, okay, first, I, Betty, will read Zoltan's talks about membership just homophonically with my own talk. So I just read his, whenever Zoltan says, is a member of, I read that as is a member of. And so then when Zoltan says, there is an empty set but no universal set, all the sets are hereditarily low, that's how Betty understands when she just says, oh right, you forgot about all the sets which were sort of, you've got the sets down here, I'm interested in the sets up there in the Boolean algebra. The second option, though, is Betty invokes the duality theorem and reads, every time Zoltan talks about membership, Betty treats Zoltan as talking about anti-membership. And now, when Zoltan says there is an empty set, of course, Betty hears that as saying, oh, there's a universal set. And when Zoltan says there's no universal set, Betty hears that as, oh, there is no empty set. And then when Zoltan says every set is hereditarily low, Betty understands that as the claim every set is hereditarily high. So the definition of hereditarily high is just what you get if you slash through all the membership signs in the definition of hereditarily low. Now, both of these, I suggest, are equally good interpretations from Betty's perspective of what Zoltan has said. Nothing favors one over the other. But that means that for Betty, if I'm right, there's no fact of the matter about what it is exactly that Zoltan is saying. So in order to make this a bit more plausible, because probably none of you are big fans at the moment of the Boolean conception of set that I'm offering, I'm going to tell a slightly different story and show how things would look in that case. Let's just skip that. Okay, so let's imagine a different case. We've got a character called Dappy, named after Dappy the, is he an N-dubs? N-dubs, yeah. Dappy has idiosyncratic views about the complex numbers.
Nobody here will know what N-dubs is unless they're
Don't care? Fine with that. Dappy has idiosyncratic views about the complex numbers. I don't know whether Dappy from N-dubs has idiosyncratic views about the complex numbers. That would be surprising to me, but it doesn't matter. My character Dappy idiosyncratically insists that the complex number a plus bi exists when and only when b is a non-negative real. So obviously we know with complex numbers we can regard them as essentially a pair of coordinates, two real numbers, one of which stands for the sort of complex part, and Dappy just doesn't like it when you have a negative complex part to it. So essentially what's happening is you represent the complex numbers with an Argand diagram, and Dappy says, no, I don't believe in any of that stuff, crosses it through. There aren't any of those numbers there. There's just the ones above the imaginary line. Okay, so that's Dappy's view, and it is idiosyncratic. So all of us think that Dappy's being a bit weird. So we might ask, how should we understand him? Dappy clearly wants to deny the existence of half in some intuitive sense of the complex plane. But intuitively, I think, we can't really say which half he wants to deny the existence of. And the reason for that is that there's an automorphism on the complex plane, a familiar one, send everything to its complex conjugate. So we could imagine Dappy as, say, trying to get rid of the bottom half of the diagram, but of course we could equally well interpret him as trying to get rid of the top half of the diagram, and everything would work out formally just as well just by using the automorphism. And informal matters, just like saying, no, I really, really mean the bottom half of the diagram rather than the top half of the diagram, clearly don't help because I mean, the picture there shouldn't be taken all that seriously. If you really take the automorphism on the complex plane seriously, the idea that it's orientated as having a top half and a bottom half is kind of ludicrous. They really should be thought of as mirror symmetric about things. So all we can do when we're confronted with Dappy is say, you've got strange views, and I respect them as a fellow human being. I understand you want to get rid of half of the stuff that is the subject matter of complex analysis, but there's no fact of the matter about which half you want to get rid of. I think that should be the correct reaction to Dappy. But if that's the correct reaction to Dappy, that should also be what Betty says about Zoltan. So when Zoltan says, I only want to believe in the hereditarily low sets, we can equally well understand him as talking about only believing in the hereditarily high sets and so forth. So Betty should say, there's no fact of the matter about what you're denying, you're just saying the subject matter is impoverished. And so when Betty now hears Zoltan say, there is no universal set, not only should she say it's an unjustified dogma, because of course we know there is a great set theory now, the one I've presented, which does give you a universal set, but it's also a dogma that has no determinate content. From Betty's perspective, Zoltan might as well have been saying there is no empty set, there is only the universal set. And when he says things like, look, the picture of sets as formed in stages vindicates the existence of the empty set, but not the universal set, she should treat him as just saying, well, but that's indifferent between saying that it vindicates only the universal set and not the empty set. So once you really start immersing yourself in this picture seriously, it's not just that you want to say people have been unfairly prejudiced against the universal set, but we can't even fully grasp the nature of that prejudice anymore. I think that's kind of fun, so I'll leave you with that thought. Thank you. Das habe ich vergessen.
I'm so intrigued by this anti-automorphism, because one of our favorite theorems in classical ZFC is due to Kunin. There's no non-trivial automorphism of V.
Yeah.
Right?
Well,
You're always suggesting in this picture you've got the identity and you have the anti.
Yeah, so I suspect,
There are two.
I haven't thought this through, but I would be really surprised if it wasn't the case that there's no non-trivial automorphism in my models. But there is a non-trivial anti-automorphism. Yeah.
And conjures up this idea that now you have this richer universe where you can kind of flip things.
Yeah, you can flip it. I have to say I don't know how.
Automorphism, you're right.
No, but I don't know how. I don't know how much other flipping you can do. I haven't explored that yet. But yeah.
So Dana was involved in some way here?
So Dana is involved, if we go, it takes too many clicks, but Dana is involved in the way I'm thinking about the second section of the talk. Oh my God, there were many, many slides. The second section of the talk where I was talking about how to axiomatize the ordinary process. Mm-hmm. So the basic setup is, if I can get up, I'm going to get RSI on my thumb now. Okay, so this theory here, well actually let me go back slightly. So there's a stage that I skipped out. So I gave you a two-sorted theory, but it has multiple primitives here. Now, if you just replace every instance of so this theory, I'm assuming here in the two sorts that stages aren't sets, that they're a distinct kind of beast. But if you instead say stages are sets, but they're a particular kind of set, but we use essentially this theory, and you replace all of the ordering relations with membership, and you replace is formed by sign with subsethood, this is almost the theory that Dana Scott writes down in a paper which comes out in 1974, but he presented it in 1967. It's slightly easier. So basically, this when you write it out in terms of subsethood, essentially it makes very clear that we're using that notion of sublative closure that I have earlier. Mm-hmm. So it's take all subsets of a member. Dana Scott offers a more complicated closure principle. Take all members of members and all subsets of members. And I don't think as a result that he needs this particular axiom here about before being a transitive relation. So he folds it all in with this. So for him, there's a slight change to it as well. So for him, a set is a member of a stage if and only if all its members are subsets of a stage which is a member of that stage. Oh, subsets and, yeah, all its members are either subsets or members of. That's it, right. So that's the very slight difference. He then says you can define away the sort of primitive second sort of using stages here, and he writes down a definition which I can't really make any sense of. And then states, this theory has as a consequence, and then essentially the quasi-categoricity results. He also, so earlier than that, he and Montague had, they had both, Montague published a few things and said, in joint work with Dana Scott, I've worked out how to do all of this. This will all come out in a book that I am co-authoring with Dana and Tarski. So there's this, there's a book in the Bancroft Library, which is at UC Berkeley, which is a completed book manuscript of a book called, I think it's just called Axiomatic Set Theory, by Montague, Scott, and Tarski. And it was literally ready to be published. I don't know why it wasn't published. I emailed Dana, but he hasn't got back to me. So if you have any way of asking him and he will get back to you, then please do, because I'd really like to know. My suspicion is it's not published because Montague dies, but I can't, the manuscript is undated, so I can't say whether that's exactly true. In that, they have a very, very long and complicated explanation where they define a notion kind of like what I've offered in terms of level, and show that it can get all of the results out that you'd want it to. But it's really heavy going. I mean, it's 13 incredibly dense sides of stuff. So Montague and Scott are kind of between them responsible for this sort of theory, but they offer a really ugly definition of level. The definition that I give instead is based on using that Montague and Scott operator there, the widening operator, which is something they develop in that book that was never published, but then plugging it into something that John Derrick and Michael Potter worked out as a way for eliminating stuff in terms of talking about histories and levels. But again, their operator for closure is more complicated. So like Scott and Montague in just that axiom that I was mentioning earlier, they take as the closure principle, take subsets of members and members of members. So if you go through and rewrite all of these axioms with, instead of just taking subsets of members, but both subsets of members and members of members, that's basically the theory they have. But it's a pain to get out these results. So this turns out to simplify it surprisingly much. But yeah, so that part of it is the least novel, and you know, I'm glad you asked about it because I want to sort of be candid and say I didn't come up with all of this. This is very much standing on the shoulders of much, you know, smarter people than me. But yeah, it is. All of this part is kind of traceable back, I think, to joint work by Montague and Scott. And it's really nice. It's a real shame that it isn't better known because it's such a natural axiomatization of set theory once you've worked with it for a little bit.
Yeah, I actually had a question about how much. I mean, if you have a universal set, something people want to do often is have things like NFU or whatever. Do you get any stratified comprehension or anything in this?
I cannot believe I will, because of the fact that types in NF and NFU get kind of tangled, and mine will not give you tangling. So mine are nicely well ordered, basically.
You clearly can't have. I mean, you clearly can't have separation as well, because otherwise you
yes. Yeah.
separate out the rest of them.
Yeah. So separation holds on low sets, and anti-separation holds on high sets. Yeah. So intuitively, every superset of a high set exists, just as intuitively any subset of a low set exists. But yeah, one of the casualties of having a universal set is the axiom of separation. But why did you want separation?
So how did the other paradoxes go? So for instance, Campbell's theorem, you don't have...
I don't have unrestricted power sets. Yeah, so remember I told you at the start of the talk, the only axioms of ZF which hold... So Boolean level theory on its own, without the extension principles, doesn't even vindicate pairs, because it's got a toy model of just the empty set in the universe, so clearly pairs fails. Extensionality holds, because that was one of the axioms. Union, the axiom of union holds, no matter what. That one's okay. Yeah, you can have pairwise intersection and pairwise union. That's good. And because the axiom of union holds, the axiom of unrestricted intersection holds. So you don't need to say take any non-empty set and do its intersection, because of course the intersection of the empty set is just V, so that's fine. But yeah, everything else fails badly. Some of them you can regain in other forms. So quite often what you can do is just take the original axiom, restrict it to low sets, not just hereditarily low sets, but low sets, and it holds. So power sets holds restricted to low sets. Foundation holds restricted to high sets, I think. Which is...
You should get by this duality thing.
Anti-power sets for high sets?
Yeah, exactly.
Yes, you do. Yes. Yeah. So anything which you write down, just do slashes through it, and you get out, which is kind of cute. So choice is a painful one in some sense. So the axiom of choice will fail insofar as the way you formulate it is demanding a choice function. And the basic reason for that is you don't necessarily want to start thinking about relations of sets, relations on sets in terms of functions as objects, because then the functions you'd always want to be low sets because they consist of pairs, and pairs are always going to look like low sets, and everything whose members are all low is itself low. But then if you wanted to have a function on a high set, the thing would be too big intuitively. So you can either jiggle around with that, or you can do what I would prefer to do and just go second order at every stage, because who's scared of second order logic? That bit's fine. Just a deductive second order logic, just a hierarchy of types floating around, no semantics. But yeah, that's a quick sketch of how those axioms play out.
So what happens with, maybe we have a little bit, but adding in things like large cardinals? So if I take a measurable cardinal, obviously I have the ultra power on the low set, but can I, and I guess if I have a measurable cardinal, I'll have an anti, if you have a model of this thing, you could then get an anti-measurable cardinal in the other code?
Yeah, well, so the duality result is, it holds in the base theory. So it will hold for, if there is a measurable cardinal, then take the statement of that, do all the slashes through. I haven't looked at really what happens in these cases. I mean, one thing I can say is, if you just take the versions of your principles and you formulate them with regard to the hereditarily low sets, so you just say, take the statement, there is a measurable cardinal, restrict all the quantifiers to hereditarily low sets. Of course you can add that. I don't know what happens if you, so you just always have to take care. I don't have a general principle. What I would quite like to be able to do is say something like this. If you have an axiom of ZF and you just restrict in some intuitive way to the low sets but not the hereditarily low sets, that's also okay. Because that's certainly the pattern for separation and replacement and a few other things. But I don't have a general schematic result there that I could state to you. So in particular, I can't tell you anything about what exactly happens about various large cardinals. But the difficulty is that once you get out of these sort of easy to state ones, like the strong, much of their statement is dependent upon other stuff that's floating around in the hierarchy, that actually keeping track of that in this context without just saying, damn it all, let's restrict it to hereditarily low sets, can be kind of a pain. I mean, as you just described, talking about ultrafilters, you're going to need to be quite careful about exactly what you mean by an ultrafilter in this new setting. But you could do it all, and it'd be a great foundation. Maybe. Yeah.
Yeah, I would like to know, so we don't have a problem with Russell paradox because we don't have separation.
Yep.
I wondered about other paradoxes, right? So I guess for the others, the answer is still that the things don't exist, right? So that is about Duality and Geneva Manov. So I guess the set of all ordinals doesn't exist, and the set of all well-founded sets also doesn't.
Yep. Yep, pretty much. So it depends a little bit about exactly how you want to define those things, though. So if you define ordinals in the normal von Neumann way and make appropriate tweaks, you'll end up with them all being hereditarily low, fairly straightforwardly. And yes, then the standard proof of the Borelli-Forti theorem that there isn't a set of all the ordinals goes through exactly as before. But the one observation you need to make is that suppose there were a set of all ordinals, then because all of its members are low, it is itself low. Now you can prove immediately that it would be an ordinal and so self-membered and blah, 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 blah. But basically, most of those ones go through in the same way. Cantor's theorem becomes interesting because you don't have for every set a power set exists. Some things that I'm trying to remember, someone asked me a question at a talk about a month ago about this, and I realized that the correct response was just to say, oh no, so here's the interesting fact. Cantor's theorem fails in this setting. I think, I'm trying to remember this, so I think V is equal to its own power set. So, there's nothing more, or at least in a suitably rich version of the theory. So there's no general concern that, of the Cantor shape there. And the reason it fails is fairly straightforward. Separation has failed. And when you prove Cantor's theorem in general, you rely upon a use of separation. You say, well, assume there were such a bijection, separate out on it, now you get a paradox. But you won't have access to separation. So you do get some funny results in that neighborhood. But just in terms of a question like, is there a set of all the cardinals? If you've defined cardinals as certain kinds of ordinals, then the answer is no, in exactly the same way as normal. If you've defined them using, say, the Scott-Tarski trick, so when you don't have choice, you want to define the cardinals as find a set of that size at lowest possible level, find the set of all equinumerous sets at that level, that will go as your cardinal. Again, there won't be any set of low cardinals in that sense. But if you do that, of course, you can also have sets of high cardinals, which are kind of fun things as well.
I guess you'll get definable class theory versions of Cantor's theorem. You can do these. Has Keanu done this? That you can have, for instance, versions of Cantor's theorem in MVG, and presumably you could sort of build an MVG-like model over.
Well, bear in mind I'm already working second order, so
yeah.
I'm already doing it MVG style for the most part. Because why not? Like, it's obviously easier. Yes, I don't know. But sorry, what was the result that you had in mind for Uskiano that I could use?
It has this result that you can prove class version of Cantor's theorem. So there are more subclasses of the universe than there are. Wait, you get it right.
Yeah, well, that sounds right.
Subclasses of the universe than there are elements of the universe.
That sounds like something I ought to be able to prove. But that just sounds like a result in second order logic rather than anything to do with set theory. That's just because the notion of subclass is just a purely second order notion at that stage.
I wouldn't ask you to make a real mess of this, Kurt. What if you weren't beginning with ZF, but constructive ZF? So you're everything with constructive.
Yes.
Then you can start.
So you mean intuitionistic, as in dropping excluded middle? So I have wondered about this. So the question is, can you do all this stuff using Heyting algebras instead?
Yeah.
Things break down, at least in terms of my ability to do anything with it at a very early stage, because just by the fact that double complementation is not idempotent.
Yeah.
So you can't even think of the universe as just being the complement of the empty set straightforwardly. And that means that anything that was nice in terms of, say, the antimorphism result about just slashing things through, all of those kind of things are going to have to fail. Right. But it's also going to make it incredibly difficult to do anything like hope that what you're doing is just working with a single set relation. So it's precisely because I can just think of the universe and the empty set as differing only in terms of slashing through the membership sign that everything works out nicely. I mean, maybe it could be done, but I haven't thought about that too much, except to say, oh, it's going to be a pain.
In terms of this view, I mean, from Betty's point of view, classical ZF people were just totally aligned. We're working in this little fragment, kind of this full.
Right.
But then there's probably even a larger universe, which arises from using a constructive logic. Where
sounds likely. Yeah, so you'll get subtle differences between.
Classical fragment of this larger constructive. theory. So in other words,
Yeah.
maybe the myopia, there are levels of myopia.
Oh yeah, I mean, so from my perspective, I would be like wholly germane to embracing that and saying, yeah, I'm not offering this as a once and for all foundation at all. It's a more sort of dialectical thing to say, if you thought that ZF was the right thing, why didn't you think that this was? And then if someone says, well, you shouldn't think this one is either, I'm like, yeah, that's more grist to my mill. I do think there might be good grounds, though, to resist that move. So, well, do I mean good? There are at least different grounds. So you might somewhere else think you have an argument that classical logic is the right logic. And if you did that, then you'd want to say, okay, I can perfectly well make sense of people who are not embracing double negation elimination, but I have to interpret them in funny kinds of ways. So I can't really just take it at face value. So someone who had that perspective would not really think that this was a short-sightedness on their part. But you're absolutely right that the intuitionist, the logician, should reply and say,
the interpretation from classical to intuition, it's like that tends to be easier.
yeah.
The constructive logics are richer than the classical.
Yes, yeah, indeed. So yeah, you're absolutely right. I mean, so the intuitionist would presumably say, using the Gödel translation, oh, yours is like the double, the always double pseudo-complemented fragment of my universe. Right. Oh, you only cared about the hereditarily double complemented.
That's your myopia.
Yeah. Yeah. God knows though what you can get out if you do. I mean, you can't characterize it. You don't want, apart from anything else, you don't want clause H, as I've put it, to be characterized in terms of omissions. Because that's already to put in a negation, and you don't want there to be a negation sign there because that's going to make everything look ugly. So I don't know how I would try to recharacterize it if I were an intuitionistic fan of the universe.
Of course, we were all very much relieved at the start when you gave us extensionality.
Yeah,
you could question that as well, right? So you could have many empty sets and many universal sets.
Do you mean if I were being an intuitionist or more generally?
Well, without extensionality, surely you could have many.
Oh, yeah. Yeah, so I suppose, I suppose one of the justifications that you can offer of, even if someone is concerned about extensionality, is you can also do some modding by equivalence classes. And then it just seems uninteresting to have bothered postulating these extra objects unless they do some extra work.
You're right.
But I'm inclined to say that extensionality just has a special case, that if you want to reason about intentional collections, that's fine, but that's just a different kind of thing than a set was anyway.
Yeah, right.
You know, maybe that's too myopic of me.
You said at the beginning, it's not set theory if you drop extensionality, it's something else.
It's my hunch. Yeah. Oh, yeah.
I was curious about the Schulze quote that you had at the beginning.
Oh, yeah.
And you at this point, I think you said that no, later you said that you want to replace form by found. I just wondered about the source of this quote. Was there anything
Get it up.
physical attached to this quote?
Oh, no. No, not at all. So, no, it's in the course of a short-ish paper called Axiomatizing Set Theory, I think. But it's at a time where the iterative conception is still not widely known outside of mathematicians who are actively working in the area. So he just says this as a sort of expository thing. I don't think he meant, at least there's certainly nothing in the text which suggests that it has an explicitly metaphysical reading. One of the things...
Does it predate Boolos, or is it contemporary with Boolos?
So Boolos is 1971, so it predates Boolos. But Schoenfeld has another kind of statement of this predating Boolos. And yeah, it's just this one is neater for my purposes to work with. But so the Scott paper predates Boolos, and I think Boolos knew about the Scott paper but didn't appropriately acknowledge it, is my kind of hunch, but I'm not sure. Yeah. And the Scott paper does it a lot better as well than the original Boolos paper, because it does give this really foundedness, which is, I think, pretty startling. But yeah, so the one reason I was being slightly cagey about moving from found to formed is that there is a certain part of this sort of constructivist story where you're creating these things, where you ask yourself something like, well, why can't you skip ahead and form those things? And you say, well, those ones you don't yet exist to form, so it's okay. Whereas told as a merely epistemological story, I guess you have less of a nice explanation of why you can't find sets which involve scatterings from all over in various different ways. So there's something about the constructivist imagery which prevents you from asking the sorts of questions you're not meant to be allowed to ask if you are trying to avoid paradox via the cumulative stage thing. Another way, though, to put things is, so part of the way I say that my story in terms of formation was adapted from Thomas Forster's story. He still talks about discovering sets, about forming sets. So one of the things that's odd for him is that V has an intentional quality to it. At the first stage, V only has two members, the empty set and V itself. But then at the next stage, it acquires new members because you formed new sets, and so those have to be in V. So he says you form it, but you stipulate that it will contain every object that there ever is going to be ever. And that, yeah, well, quite. Is exactly the right response to that. And that leads him to a bit of a problem, because then he says, look, maybe there is an asymmetry between the empty set and the universal set, because one of them is intentional and the other one isn't. I say, just talk about what you discover instead of talking about what you form, and then there's no intentionality to it. You just learn more about what the universe has in it, but you equally learn more about what the empty set doesn't have in it, and that's perfectly symmetrical. So, again, no difference.
This comment is totally unrelated, but it's sort of popped into my head.
Yeah, with Sean Walsh.
I was struck that in stability theory, the important notions are to not have the obvious property, to not have that sort of property, to not have it. So somehow, it's this funny intuition. I mean, you have these sort of, there's not really a symmetry in mathematical properties, is there? To not have the property is often very artificial, but to have the property seems very intuitive and compelling. I just was intrigued that in some areas of model theory, it's like the classifiable theories. These are the ones which do not have this, and
yeah.
I don't know, it just made me think of your negation.
Oh, I see. Oh, well, so for that case,
the level of properties instead of the level of set.
I mean, I think in that case, it's kind of intuitive why, when you realize that basically having any of those properties makes your theory rich enough to do appropriate bits of coding that then make everything go really haywire.
Okay.
So that's really all you're doing. And then, obviously there are interesting and complicated details about what that comes down to, but you're ruling out the things which give you the power to set up certain kinds of definitions. But yeah, I mean, I think you're right. I think though one of the intuitions that people have here is that there should be somehow there's something more natural to membership than non-membership.
But I understand being a cow better than I do not being a cow. I mean, there's so many ways to not be a cow.
Right. So that
cow,
I think there are a great many ways of being a cow. There are Holsteins and there are Friesians. No. But I do know what you mean. I guess the difference between I don't know whether there are as many ways to have something as a member as there are ways to not have something as a member, or whether that is just really to be thought of like it's a graph and either you draw an arrow or you don't, and it's no more dramatic than that kind of thing. Yeah, but I think people do have that sort of rebellious intuition there. There must have been something more natural about membership. We define things in terms of their members, not in terms of their non-members or something like that. But I mean, extensionality works just as well if you regard it as defining things in terms of their non-members. Sets are identical if and only if they emit the same things. It's just a trivial variation of the axiom of extensionality. So again, non-membership is fine as a way of defining things.
Anyway, thank you once again.
Thank you, sir.